This is my third video explaining the stack machine from Nand2Tetris. In my past two videos, I explained the stack machine abstraction, and in this video, I will introduce the stack machine implementation. In my next and final video in this series, I will explain how the implementation works. To demonstrate the stack machine implementation, I will walk through SimpleAdd and StackTest again, but unlike my previous video, where I focused on the stack, which we can see here on the left, in this video, I will be focusing on the global stack, which you can see here in the center of the screen. As I walk through these programs, I'll be following along with a video with index cards, which I have here on the right. And in this video, we can see a piece of paper with the numbers 256, 257, 258, and 259 written on it. And these rectangles, they correspond to these memory addresses, 256, 257, 258, and 259 in the global stack. Also in this video, I have this index card with SP written on it, and that corresponds to the stack pointer, which in the global stack we can see as the memory address that is highlighted in yellow. In my first video in this series, I mentioned the stack pointer, but I chose not to explain it then. And the reason I did that is because the stack pointer didn't fit in with my analogy of using index cards to explain the stack machine abstraction. But now that we've reached the stack machine implementation, we need to understand stack pointer in order to follow what is happening in the global stack. There are four things I want to mention about stack pointer before we go forward. The first thing is that stack pointer always points to the next available memory address where values can be pushed to. The second point is that after we perform a stack operation, we move the stack pointer to one memory address above the function's output. The third idea is that all values in the global stack that come before the stack pointer are equivalent to the stack machine abstraction. And the fourth and last idea is that all values in the global stack that come at or after the stack pointer can be ignored. And that's a lot to take in. So in order to understand this better, we need to see some examples. So why don't we go ahead and look at SimpleAdd. I have SimpleAdd loaded into the virtual machine emulator, and I'm going to walk through this program the first time with my video using index cards. So I'm going to expand this window so we can see it better. And then to start, we can see that our first operation is to push constant 7 onto the stack. So I'm going to do that on the left. So now we've just pushed constant 7. And we can see that here in the abstraction. And I'm going to do the same thing on the right. So first, I look at where the stack pointer is pointing, so that's where I know where to push to. So I push a 7, and then I increment the stack pointer up by 1. And then our next operation is to push constant 8. So I look, let me hit this button here on the left. So now we've pushed constant 8 onto the stack, and we can see that here in the abstraction. And then in my video on the right, I'm going to look at where the stack pointer is pointing, which happens to be 257, so I know where to push to. So I push this value to 257, then I increment the stack pointer up by 1. And then our next operation is to add the top two values in the stack. So I do that on the left, and then we can see here in the stack that we have a 15. And then I can do the same thing on the right. So what I'm going to do here on the right is I'm going to come with an add card, and the add card is just something that that's how I like to visualize what happens, but in the global stack there is no add card. So I just wanted to point that out. But what I'm doing here on the right is that I'm overwriting the first input value with the output of the operation. And then I decrease the stack pointers that is pointing to 1 above the output. So let me say that one more time. I overwrite the first input, which happened to be 7, and then I decrease the stack pointer down so that it is 1 above the output. And the reason we do this is that, this is the computer's way of getting rid of the inputs. In my previous two videos, I visualized this by merging the cards together and stapling them. That's how I got rid of the inputs and was only left with the outputs for the function. But the computer does this a little bit differently. The computer does this by first overwriting the first input and then decreasing the stack pointers that it is 1 above the output of the function. And it does this because every value that is at or above the stack pointer in the global stack is ignored and excluded from the stack machine abstraction, which we can see here on the left. even though we have this 8 here, we don't see it in the stack because it is at or above where the stack pointer is pointing. So that's everything I have to say about this, and then I'm going to repeat this explanation, but looking at the global stack. So now I'm going to repeat this example, but focusing on what happens in the global stack. So to start, we can see that the stack pointer is pointing to memory address 256, and that is why this memory address is highlighted in yellow. So our first step is to push constant 7 onto the stack, and I'm going to follow along with my video on the right. So here I push the 7 onto the stack and increase the stack pointer. And then I can do the same thing, but with 8. So I push an 8 and increase the stack pointer. And then on the right here, I push an 8, then increase the stack pointer. And then I'm going to add the top 2 values in the stack and then decrease the stack pointer so that it's 1 above the output of the function. So we add the top 2 values, and now we're left with a 15 and 256. And our stack pointer has decreased so that it is 1 above the output of the function. So now the stack pointer is pointing to 257. I'm going to do the same thing in my video on the right. And then one thing I wanted to note was that because our stack pointer has decreased, everything that is, let me rephrase that. So everything that is at or above the stack pointer is going to be ignored by the abstraction. So that is why, even though we have an 8 here that is in the global stack, since it is at the same memory address as the stack pointer, it is ignored in the global stack, and that's what it's ignored in the abstraction of the stack, and that's why we don't see it here on the left. Now I think that's everything I wanted to say about this, and now I'm ready to move on to the next example. So now I have StackTest loaded into the virtual machine emulator, and then I'm going to work through the first few commands here using my video with my index cards here on the right. So I'm going to open this up, expand this window so we can see it better, and then we can see that our first operation is to push constant 17 onto the stack. So let's see what that looks like. So here I push the constant 17 onto the stack where the stack pointer is pointing, and then I increase the stack pointer up by 1. And then I repeat that again where I push another 17, and then I increment the stack pointer up by 1. And then now I check if the top 2 values are equal, and we know that 17 is equal to 17, so the output of this function is going to be -1. So I overwrite the first input value with -1, then I decrease the stack pointer so that it's pointing to 1 above the input value. 1 above the output value. And so our next operation is to push constant 17. And so we're pushing a 17 onto wherever the stack pointer is pointing, and there happens to already be a 17 there, so that you don't really notice the difference, but we are actually doing something. In the global stack, this won't be very clear, but I want to make sure that it's clear here. So we push a 17, then we increase the stack pointer, and then we push a 16, and then increase the stack pointer again. And then we check if the top 2 values are equal, and they're not going to be equal, so we overwrite the first input value with 0, which is the output of the operation, and then we decrease the stack pointer so that it's pointing to 1 above the output value. All right. So now I'm going to repeat the same thing, but in the global stack. So now I'm going to repeat what I just covered, but now focusing on the global stack. And I'm going to follow along with my video on the right at the same time. So first we push constant 17 onto the stack and then increase the stack pointer by 1. So then I do that on my video on the right. And then we push another constant 17 and increase the stack pointer by 1, and I do the same thing on the right. And then I check if the top 2 values in the stack are equal, and then I overwrite the first input value with the output. And do the same thing on my video on the right. And then now I overwrite the value where the stack pointer is pointing by pushing a constant 17, though in the global stack we won't notice that. We won't see anything because we're overwriting 17 with 17, so you won't notice any difference. So that's why now we still have a 17, but we've incremented the stack pointer up by 1. And we can also see it here on the left, where now we have a 17, where we didn't have one before. And so now I'm going to do the same thing on the right, where I push a 17, then increment the stack pointer up by 1. And then here in the global stack, I'm going to push a 16, then increment the stack pointer up by 1, and do the same thing on the right. And then now I'm going to check if the top two values are equal and overwrite the first input value with the output of the operation. So that's where this 0 comes from. And then I'm going to do the same thing on my video on the right. And then I just want to note, like I did in my previous example, that because the stack pointer decreases down, that is why we ignore the 16, and that is why the 16 doesn't show up here in the stack abstraction. It only shows up here in the global stack. Because as this program keeps going, eventually we're going to overwrite the 16 with a new value. And I'm actually going to skip the next few instructions in the program because I think it's all more or less the same. I think that if you've understood what I've said up until now, everything else here should make sense. So I'm actually going to skip down to line 27 in the program. So I've now skipped down to line 27 of the program. And we can see here in my video on the right that now we're looking at memory addresses 265, 266, 267, and 268, corresponding to 265, 267, 267, 268. And then one thing I forgot to in my video is that I forgot to have an index card saying 32,766 in address 265, though it's not really important anyways because that is where the stack pointer is pointing and we're going to overwrite it with a new value anyway, so it didn't matter what was there. But that's just something I forgot and I wanted to mention that. So that's why that isn't there. And so now I'm going to walk through this with my index card. So I'm going to expand this window and then we can see this program here. So our first operation is to push constant 57 to where the stack pointer is pointing. So I'm going to push a 57 and then increase the stack pointer up. And then the next step is to push a constant 31. And then I do that, increase the stack pointer up, push constant 53, then increment the stack pointer up. Then I add the top two values in the stack. So I replace the first input value with the output, which is 84. Then I decrease the stack pointer so that it is 1 above the output. And then I push a constant 112 and overwrite whatever was in 267. And then I subtract the top two values in the stack. So now I overwrite the first input and then decrease the stack pointer. And then in instruction number 33, this is something I want to take a moment to explain, is that neg, it's a unary operation, so it only takes one input. So here we're going to see that I'm going to overwrite the first input value, which is the only input value. And then the stack pointer is going to stay in the same place because it is 1 above the output. And since there's only one input and one output, since there's only one input, then the stack pointer doesn't actually change position. And then I'm going to take an AND of the top two values in the stack. And this doesn't make sense, but since we're working in a low-level language, we can do this. And then I decrease the stack pointer, so it's 1 above the output. I push a constant 82 to where the stack pointer is pointing. Then I increase the stack pointer up by 1. I take an OR of the top two values in the stack, which, again, this doesn't make sense because we're taking an OR of integers, but we can anyways. Then we get a 90 and decrease the stack pointer. And then the last operation is to take a naught of the top value in the stack, which is 90. And this is another unary operation. So I just overwrite the first input with the output, and the stack pointer stays the same. It stays in the same place because it is 1 above the output of the operation. All right, so that is everything I have with the index cards. And now I'm going to go back again and look at the global stack. So now I'm going to repeat my explanation, but this time focusing on the global stack and focusing on memory addresses 265 through 268. And then again, I'm missing my 32,766 in my video on the right, but that's not very important anyways. So my first operation is to push 57 onto the stack. So now we have a 57 pop up. Actually, I'm going to slide this down so we can just focus on only what's important. And then I'm going to repeat the same thing on the right, where I push a 57, then increment the stack pointer by 1. And then in the global stack, I'm going to push a 31, increment the stack pointer by 1, do the same thing on the right. Then on the left, I'm going to push a 53, and then doing the same thing on the right. And then in the global stack, I'm going to add the top two values in the stack. So now we get this 84, and we decrease the stack pointer down by 1. I'm going to do the same thing on the right. And then I'm going to push a constant 112 to where the stack pointer is pointing, and that happens to be memory address 267. So this 53 is going to get overwritten by 112. So that's where that 112 comes from. Then we increment the stack pointer up by 1. And I'm going to do the same thing on the right. And then now I'm going to subtract the top two values in the stack. So now we have that negative 28 in memory address 266, and then we decrease the stack pointer down so that it's 1 above the output of the operation. And do the same thing on the right. And then in line 33 of the program, we're going to take the negative value of the top value in the stack. And so we can see that first we have a negative 28, and now that is about to become a positive 28. So we see a positive 28, and then the stack pointer stays in the same place. Or yeah, it stays in the same place because it stays at 1 above where the output is, 1 memory address above the output. I'm going to do the same thing on the right. Now I'm going to take an AND of the top two values in the stack, and then that leaves us with 24 in memory address 265. And now the stack pointer is 1 above the output of the operation. I'm going to do the same thing on the right, where now I overwrite the first input with 24 and decrease the stack pointer so that it is 1 above the output. I push a constant 82 onto the stack where the stack pointer is pointing. So now we push an 82 and then increment the stack pointer up. And I do the same thing on my video on the right. Now we take the OR of the top two values in the stack, and that leaves us with 90 in memory address 265 and the stack pointer pointing to memory address 266. I do the same thing on the right. And then our final operation is to take the NOT of the top value in the stack. So now that 90 is overwritten with a 91, which is the output of the function, and the stack pointer stays in the same spot because this is a unary operation. And I'll show the same thing on the right. All right, and then that concludes this demonstration, and I just want to note here that in the stack abstraction on the far left, the 91 is the top value in the stack, and then we can see this 91 here in memory address 265. And we can see that everything that is at or above the stack pointer is excluded from the stack machine abstraction. So that is why 82 and 112 are not here in the stack machine abstraction on the left.